So I thought a video might be an easier way of you looking at, or me explaining the bending moments in your design. We had two problems. Well, this is the second part of the problem we're going to look at. But the first part of the problem was this: you've got this beam across your design, and you've got two of them, top and bottom, and you were asking about how I would analyse their bending moment, because obviously there's going to be a weight acting here, that's going to act downwards, and these are obviously going to flex. And the question is how do you analyse that and make a materials choice? And we sort of talked about that it would just be a sort of, not guesswork, but you would sort of do an educated guess. And I want to sort of illustrate this. So I've been on the internet and I found that you can buy, and this is the thing about stock material, you can buy. So I'm going to sort of just draw this to scale, just give you an idea of how big. So this is what you can actually buy. It's 2.5 by 2.5 centimetres, so 25 millimetres, so it's an inch square. Aluminium, by the way, is nearly always imperial rather than metric, but they do the equivalents. And you can buy this, and it's got a wall thickness of 1.5 millimetres, like so. Okay, now we're interested in this deflection here. Let's just find a pen to illustrate this. I'll try and keep this reading. So we're interested in this deflection there, and the equation for that deflection is the force being applied. Okay, so we've got 50 kilograms, which is effectively 500 newtons. It's actually 490, but let's go 500. What I'm going to do is I'm going to round everything up so you can look at these numbers and then you can work them more accurately with decimal places to give yourself a more accurate answer. So we've got 500 newtons, so effectively you're going to have 250 newtons acting on that part, and another 250 newtons acting on that part. So I'm actually only interested in this bit at the moment. So the force is going to be 250 newtons. The length is this. Well, it's between these 2 points actually, but notionally we're going to call that 1.5 metres. So that's going to be 1.5 metres. It's divided by, now this number 48 is effectively what we would call an unpinned or free beam. And what they're talking about there is if you've got a beam bending and it's simply supported, this can go down, as the beam bends down, these ends are free to move upwards. Now if we treat it like this, we can use this very simple formula. And to some extent, this is going to be loose enough to allow that to happen. So we're good using this one. We can justify this. It's going to be the Young's modulus for aluminium, which is 70 GPa. Check that. I think sometimes it can be seen 69. We're effectively going to use that. Okay, it's 70 times 10 to the 9. That's going to go in there. And then we're going to use I, which is the second moment of inertia. So for this particular piece, this beam, if you will, this cross-sectional area that we're talking about, it's 25 by 25. Now the formula is base times the height. There, base, height, cubed, divided by 12. Okay, so we're going to work this out down here, and then we're going to put it back into the formula here. Okay, so let's do that. It's 25 by 25 cubed divided by 12. This is in millimetres. Okay, so to convert this, I'm going to simply go 0.025 0.025, so it's now in meters, because I like to do everything in meters because we've got the length in meters and we work in meters, so let's stick to that. So that's the outside, and we need to take away this inside area, so it's going to be minus, now the inside is going to be, well, we're going to take 1.5 millimeters that side, 1.5 millimeters that side, so we're going to be minus 3 millimeters. So it's going to be 0.022 times 0.022 cubed. divided by 12. Now I know what you're thinking, that's effectively 0.025 to the 4. That's 0.0224 divided by 12. That's the easiest way to do that. And we'll look at these two numbers. So I'll borrow a calculator for a second. Put that on here. So I'm going to 0.025 out of 4. Okay, divide that by 12. Turn it into an engineering number, so I've got a magic engineering button on the calculator, and it's 32.6. That's 32.6 times 10 to the minus 9. I'm going to take away the inner area. So 0.022 to the 4. Divide that by 12. Again, engineering button to turn it into minus 9. So it's 19.5 times 10 to the minus 9. So the overall is that, take away that, minus 32 minus power minus 9 is 13 times 10 to the minus 9. Now, as a deflection, I'm curious to know what that would give us if we take that number and put it back up here. We've got a force of 250 newtons multiplied by a length of 1.5 meters, which we're going to cube, divided by 48 times 70 times 10 to the 9 times 13 times 10 to the minus 9. That's going to give us our deflection. So if we just crunch those numbers, so we're going to get 827 on the top, and we're going to get 43680 on the bottom. So that's going to give us a total deflection of 0.0189. So that's in millimeters. That's 20. It's 19. It's 20 millimeters. That's 20 millimeters of deflection. That's a lot. So over your 1.5 meters, your deflection would be that much. That's a no-no. Okay, so we know now that 25 millimeters. Now, in bending, it's this depth that's the key. If you could make this deeper, then you could reduce that 20 millimeters of bending by increasing this depth. Okay, so the question is, what's an acceptable depth? So let's look at doubling because you can buy aluminium tube. So I'll draw another scale one. You can actually buy this as a 50, which changes the dimensions of your design. And this is the thing about engineering. I am curious to see what that's going to reduce your, because it's not just going to reduce it by a little bit, it will significantly reduce it. So if we went for this size, and this again, this is to scale, so it gives you an idea of what we're talking about. That would be quite a chunky piece of aluminium going in that direction. But you know, you can bolt through here and you could mount your and you've got two of them, but I'd be interested to see how this works out if we put that double height into the equation C. So that's what I'm going to do now. I'm going to switch over to a blue pen. And let's have a look at this again. So we're now looking at, so we had 0.025, we're now looking at 0.05 here, to the 4 divided by 12, and we're going to take away, well, we've got 1.5 millimeters there, and that's, we're taking away 3 millimeters. So that's going to give us 0.047. So 0.047 there to there. So that's going to give us 520. Let's just leave it 520 because I'm dramatically rounding here, but it's a rough figure. 520 times 10 to the minus 9. I'm going to take away 406.6, so let's just round that again. Let's go for 406. 10 to the minus 9. So if I take that away from, so I'll go 520 minus 406 would give me, so I've got 114 times 10 to the minus 9 meters to the 4. So it's a significant. So I've doubled the height, but I've dramatically increased, factor of 9 or 10, increased the stiffness. So I'm going to wonder how that changes this deflection. So we'll look at that calculation now. So that would be, we've still got 827 on the top. I'm going to have 48 times the 70 times 10 to the 9. Times, now it's going to be 114 times 10 to the minus 9. So that's going to look like 827 on the top divided by, so we're going to be looking at 3,83040. 827 divided by 3,83040. Okay, 0.00215. It's 2. That's basically, it's 2 millimeters. So effective bending across. If you had a beam that was 50 millimeters here, 50 millimeters here, 50 millimeters here, the effective bending of 50 kilograms across 1.5 meters would only be 2 millimeters. That much bending, that tiny distance over 1.5 meters, it's hardly going to be noticeable. That's your maximum. So this sort of sets the position, says, well, okay, this beam going across here, if I pull this diagram right down, if this beam here, that needs to be that dimension. Now, there is another solution to this, because you do have control, is you change this. You change the E, and you switch to something like steel. And you go back to steel tube, and you go for a smaller dimension. This is that first analysis that says this is the decision I'm making about this particular beam, because once that decision is made, you can then make an effective decision about how big this space is going to be. Now, all of that said, that's not going to change the fundamental question that we started with, which is you've got 500 newtons acting at a distance from the wall. So the next video that I show you, we're in this situation. There's your wall. Somewhere at some distance from the wall, you've got 500 newtons. You've got a mass acting due to gravity headed in that direction. and you've got some sort of structure that's trying to hold that against the wall, like so, when effectively it's trying to pivot away. It's trying to go down, and it's trying to pull in that direction against this bolt. And in the next video, that's what we're going to have a look at with you. Hope you found this useful. Don't be afraid to ask any questions. Find me an email back if it doesn't. But also don't be afraid to use this to justify your design decisions as an engineering analysis. Okay, and that's a nice 15-16 minute video, and I hope that's okay for you.